Welcome to tutorial on the Bjt Biasing Circuits Part 3. And now in this tutorial video, what we're going to basically learn is that we're going to learn about the about the emitter biasing technique. Okay, so I'm just going to pen it down over here. Emitter bias. Okay, so now this particular type of bias that I'm going to talk about over here, this sort of a bias technique, okay, is comparatively way better than what we have seen in the case of the the base bias or the collector bias, whatever. So by far the emitter bias that we're gonna learn over here, you'll basically see how this sort of bias will basically maintains the operating point rock solid. Okay, so I'm just gonna bring the circuit over here. There you go, that's a circuit over here. And now if you're just interested in knowing about how this circuit basically works, so let me just tell you that this circuit's got three resistors. Alright, so here we have the emitter resistor that's denoted with the symbol of Re. Okay, and this is the particular resistor that helps in stabilizing the operating point of this particular BJT amplifier. Okay, and then we got the collector resistor as you've seen in the previous tutorials, and we also got the base resistor. So just kind of don't mind that, my slip of tongue. So here we got the base resistor RB. Okay, and now we have the base resistor basically connected to a voltage source that is gonna forward bias the base emitter junction, so that we'll have the base emitter forward bias voltage developing across this. Okay, so we have here our VBE. Alright, so okay, so speaking from this point of view, we know that if we just take the input part of the circuit, okay, where we also find that there are two capacitors over here. That's the input signal coupling capacitor, that's the CI, okay, and the output capacitor, that's the output signal decoupling capacitor. Just helps to remove the DC component of the collector emitter voltage. Okay, so yeah, that's all. And now if we just take a look at the input part of the circuit, it just contains the input loop, since we've just drawn the circuit this way. So if we just take the input loop over here, which contains the base resistor RB, the the voltage drop across that of RB, and then we have the base to emitter forward bias voltage, that's VBE, and also the voltage drop across that of RE. So you can see that due to connecting the base resistor to the base terminal from a voltage source VBB, it's quite obvious that there would be a base current flowing into the base terminal from that of the source VBB into and in through the base resistor, and finally into the base terminal of the BJT over here. So we can just understand that there will be a voltage drop across RB that will be given by IB RB. Okay, and also if you just take a look at the output part of the circuit, okay, now whenever we forward bias the BJT over here, it's gonna have a zero signal collector current. Okay, that's the collector current when there's no input signal through the capacitor CI. Okay, so we're gonna have a collector current back then, which is obviously a DC value, and then this is gonna enter into the BJT and will come out of the other end as the emitter current. Okay, so there's gonna be also a voltage drop across that of the emitter resistor RE, which would be given by IERE. Okay, and this so if we just take the voltage drop across the emitter resistor, the voltage drop across that of the base emitter junction, and also the voltage drop across that of the base resistor, then if you just add them up together, then we're gonna get the magnitude of the voltage source VBB. Okay, and this particular thing can be obtained from applying KVL conditions at the input part of the circuit. Okay, so the base resistor and the emitter resistor, these are the the most important components when it comes to the emitter bias circuit. Alright, so Now that we have this particular equation over here, we can also get to know, or rather understand from this particular figure over here, that the collector current and the base current together enters into the BJT device and comes out of the other end as the emitter current. So we can just state this, that the emitter current, sorry there, that's not easily visible. That's better. So the emitter current would be a sum of the base current and the collector current as well. So if we just use this sort of use this condition over here in the equation that we obtained for the the input loop, let's just call this one as equation 1 over here. So if we just substitute equation 2 in equation 1 in the place of the emitter current, then we're going to get VBB equals to IBRB. Okay, and then we just put this over there, so you get IB plus IC multiplied with RE plus that of VBE. So there you go. So this is exactly the equation that we'd be using over here, and from this particular equation we're going to obtain the value of the base current. So if we just try and find that out over here, then we're going to get IB would be equal to VBB, okay, minus that of VBE. All right, and we'll also have minus that of ICRE, and the whole thing would be just basically divided by basically RB plus that of RE. Okay, so there you go. So from this particular equation that we had over here, we came to deriving the expression for the base current if we just take the input part of the circuit over here. Okay, so speaking from the design point of view of the circuit, you can also get to know the base current if you know the transistors beta and the value of the collector current. Okay, so that's quite an experimental way of determining, and here we're just adopting basically using the theoretical calculations in order to determine the value of the base current over here. Alright, so before we move into the further details, okay, so let me just tell you that in order to explain how the circuit basically works, we can see that by connecting the resistors over here and configuring the circuit this way, is going to set up a base current IB whose value will be given by this expression over here. We're just going to call this one as equation 3. Okay, that's better. So the equation 3 gives us the value of the base current that's supposed to be entering into the BJT device. And now if we have an input signal over here, okay, with smaller magnitude input signal, then it's quite obvious that we would basically expect a larger amplitude output signal from this particular circuit. But in order to get the output signal this way, it's quite essential for this particular signal to be amplified within the BJT. Alright, so what happens over here is that the emitter resistor that's placed in between that of the emitter terminals and the ground, what this basically does is that it helps in maintaining a particular voltage drop across itself due to the emitter current flowing through the emitter resistor. And this particular voltage basically helps in keeping the operating point rock solid. And how is that? It's because of the fact that in case of a CE mode of BJT operation, we know that the collector current and the emitter current, they are almost equal in magnitude. Okay, we can just blindly take them as equal to the equal to each other. They're approximately equal to each other. So speaking from that approximation, if we would just think a little bit, then we can get to understand that since the emitter resistor over here what is placed, okay, so what it basically does is that it helps in limiting the value of the collector current. So it just helps in limiting the maximum value of the collector current that would basically flow through the BJT circuit. So by maintaining the emitter current at a particular within a particular limit, it's quite obvious that since the emitter current remains within a particular limit, so it's quite mean, it's quite natural that the collector current would also remain within the same limit, since they're both, approximately equal to each other. So the the emitter resistor over here helps in keeping the collector current within limits, and it doesn't let it, vary a great deal. Okay, so there are lesser chances of the collector current to increase to a large value. All right, so now due to this phenomena that's going to take place over here, the collector current being restricted within limits, it's quite natural that the collector emitter voltage, which is going to develop across that of the collector and emitter terminals, that's VCE. Okay, so the collector emitter voltage, we know that the operating point is given by, well, the collector current and the it's given by collector current and the collector emitter voltage values. So if we just maintain the collector current constant, then from the output characteristics of a BJT, if you just take a look at the active region of operation, it'll be quite obvious that the collector emitter voltage would also remain constant. So let me just explain the concept a little bit more. Okay, just hold on a second there. Okay, so we have a picture of the BJT output characteristics, and as you all had learned in the previous tutorials where I just explained how the operating point varies when the transistors amplify. Okay, let's say we have an operating point. Let's say this is our active region. Okay, so this is our active region of operation. Okay, I'm just gonna pen it down over here. Okay, there you go. So now in the active region of operation, let's say we take this point. Let's just call this one as VCE2, IC2. Okay. So if we're just taking this as the operating point over here, let's just call this as Q2. Okay, so then in this case what will happen is that since during the amplification of an AC signal, the Q points would basically vary in vary about the position. Okay, the values of the collector current and the collector emitter voltage would basically vary to a great extent along with the load line. Okay, so in that case what will happen is that there is a tendency of due to sudden variations, it changes in the value of the transistor beta, the base emitter voltage, and also the leakage current in the reverse bias collector junction. All these factors can basically affect the amount of collector current that can flow. So if we just take this example over here, then I might explain that, well, by using the emitter bias configuration over here, since the emitter resistor maintains the value of the collector current within a definite limit, so it's quite obvious that the collector current has lesser degree of variation. So if the collector current varies less, then it's quite natural that the collector emitter voltage would also vary less. So for this particular collector, value of the collector current over here, the collector emitter voltage is about, let's say, VCE2. So if IC2, the collector current over here doesn't vary much from its maximum value, that is IC2, then it's quite obvious that the collector emitter voltage would also remain constant, fairly constant. Okay, so we can see here, or rather get a flavor that this sort of a biasing technique looks quite promising than what we have seen previously. So if we just try and find out the stability factors, then we're going to use the equation, the basic equation for the CE mode of the transistor configuration, which says that IC, that's the collector current, is equals to beta times that of the base current plus that of beta plus 1 times that of ICO, that's the leakage current. And we have taken the ICBO, that's the basic the leakage current available in the reverse bias collector junction as well, and generalized it as ICO. So we're basically going to use that over here also. So if we just take the value of the base current from this equation 3 and substitute in this equation 4, then we're going to obtain an equation which is going to yield us a fairly large value for the collector current. So let's just write that down over here. There you go, that's our equation. And if you just take this particular equation over here, so this is the most important equation that we require from the point of view of finding out the stability factor. So let's just call this one as equation 5. And well, if we just go forward and well find the stability factors from that of the equation 5, then we'll get for the value of S, that's the stability factor representing the variation of the collector current with respect to the variation in the the leakage current in the BJT collector junction. Then this will basically yield us with an expression. Alright, I'll use a different color over here. So this is going to yield us with an expression by taking the partial derivative of this equation 5, and we're going to get an expression that would look like something like this. Okay, so you have this expression which well basically yields us the value of S. Okay, and here we got it as well, beta plus 1 multiplied with 1 plus the base resistor divided by the emitter resistor, and the whole thing by beta plus 1 plus RB by RE. So you can see that well this is fairly quite a length of an equation over here, I mean expression over here, and we can just get an idea that well this particular expression is basically going to yield us with lower values of S compared to what we saw in the previous tutorials. Okay, so let's keep that hope in mind alive, and let's just go forward and well find out the values of the other stability factors as well. So we'll get the value of S dash and S double dashed. So let's just find out the value of S dash first, which is given as well the del IC by del VBE. So if we just go forward and take the partial derivative of equation 5 once again with respect to that of VBE, then we're going to get an expression. Okay, we're basically going to get an expression that would look like this particular thing that I've written over here. So other than that, we also need to find the value of that of S double dashed. So that just gives us the variation of the collector current versus the variation in the transistor beta. And well, using this biasing technique, we're going to obtain the expression once again for possibly this particular expression over here. Well, now that's one hell of an expression. Okay, it's really big. And apart from that, it also contains certain variables that I mean two expressions where we can see that it is the same expression as that we got in the case of the stability factor S over here. And that's why in order to just well keep the expression comparatively shorter, okay, so that is easier to write down, we just well replaced this part present in this equation with the symbol S. Okay, so that we know that the value of S is just the expression of S is just present over here. All right, so these are the various three types of expressions that we would possibly get for the three stability factors in the emitter bias type configuration. And now, well, this sort of arrangement that basically looking at the expressions over here, it gives us an idea that we're basically going to obtain, or rather we're basically going to have good news for us in the way that the stability factors are possibly going to have well lower values that depend less on beta. Although beta is present in all the expressions that we have over here, but still due to the higher values of the magnitudes of the resistors and all present in the denominator, it's quite understandable from this point of view that the stability factors are going to have lower values. So let's just check out our advantages and disadvantages of using this circuit. Okay, so we're here, and well, as seen from the circuit description and also the expressions of the various stability factors, we just get an idea that well, the circuit is going to have better Q point stability compared to the others that you've seen before. Okay, so in the point number 1 of the advantages section, okay, it says that well there's marked improvement in Q point stability. So that's quite obvious since the collector current doesn't change as much, so it's quite natural that the collector emitter voltage would also remain fairly constant. And of course at point number 2 this has been highlighted over here. It says that well I see that the collector current is well almost unaffected by the variations in the transistor beta, the base emitter voltage, and due to the and this could be attributed to the inclusion of the emitter resistor RE over here. All right, and well, the disadvantages, well, of course, there are two sides of a coin, so it's quite natural that we'll have disadvantages as well. So we have in point number 1 says that the design process of this circuit is quite delicate, so there's no margin of error. So if this circuit could be designed properly, then let me just tell you, you're gonna have a good time with your amplifier. And then in number 2, there is a comparatively higher values of power supply voltage required. So that could be understood from the circuit over here, since there are 3 voltage dropping areas over here, one across that of the collector resistor, then across the emitter resistor, and then finally across the collector and emitter terminals. So due to in order to supply fair amounts of voltages across all the 3 sections, we need higher values of VCC, maybe in the order of about, let's say, 15 to 20 volts. All right, so apart from that, let me just tell you that whenever we have an AC signal coming in over here, so it's quite natural that the collector current would vary. Okay, maybe not as much, but it'll still vary. Now, since the collector current would vary with the increase or decrease of the base current, the collector current would vary as well. So it's quite natural that the collector current being approximately equal to the emitter current, as we've stated over here, that there would be certain variations in the voltage drop across that of the emitter resistor. Now that is not desirable. So what do? Okay, so we do a modification over here. So what we do is that we just include a capacitor. Okay, so I'm just gonna draw that over here. So you're basically gonna include a capacitor that's gonna be connected across that of the emitter resistor. So the capacitor is gonna be connected in parallel with RE. Let's just call this one as CE. So this particular capacitor that we just call CE is known as our bypass capacitor. Okay, so I'm just gonna write that down over here. It's the bypass capacitor. All right, so we need this capacitor to let the AC components of the collector current to basically bypass through to ground without passing through the emitter resistor RE. Okay, and also let me just tell you one more point over here. I'd like to state it in the disadvantages section, is that we need for the circuit to be properly functional, we need high values of the emitter resistance. Okay, so if we just compare the advantages and the disadvantages over here, we can see that the advantages are far more useful, and they outweigh the disadvantages, which is just minor issues. So with that, we just wrap up our discussion on this particular circuit over here, and we'll see you in the next tutorial. So till then, just keep watching, and thanks for watching this tutorial video. So goodbye for now.